With that, I'd like to introduce Jason Livingood, who'll be presenting dual queue networking, how to prepare your network to support L4S and NQB. Jason is a vice president at Comcast and is coming at us today from Philadelphia. This is Jason's first time presenting at NANOG, and he's been a regular attendee, though. So it's a pleasure to have him speaking. Welcome, Jason.
Great. Thank you. And even though I'm from Philadelphia, I come to you today from Washington, D.C. I was there yesterday talking about not just low latency, but routing security. And I can tell you it was very difficult trying to explain routing security to lawyers, not saying like ROA and RPKI and whatever, and trying to use better descriptions. So I'm going to talk to you today about dual queue networking. So this is a technology that is coming out of the IETF, and we at Comcast have it in field trials right now. And I'm going to sort of explain, what latency is and so on. The first step is, everything that a lot of network engineers believe about end user internet performance is mostly wrong. And in part, that's because there's been this focus for many, many years, probably 25 years, on bandwidth, on speed to the end user. And as it turns out, that's a really great proxy for end user quality, but it's a kind of an indirect proxy, and it's not the only factor these days, especially with more real-time interactive types of applications. And we have found that almost all of the end-user QoE problems that we encounter with customers are not due to limited bandwidth. It's due instead to latency. But the problem, of course, is that nobody really understands exactly what latency is or exactly what latency we're talking about. Today, most people, obviously, latency is delay. No one likes delay. You don't want to wait for something. You don't want a web page, that's going to take a while. You don't want that to take time. But most people think of latency as what is really idle latency. So you run a ping test, you're watching what the round trips look like, but there's not a lot of other traffic that you're competing with, and you just have this one flow. What really is important, though, is what's called working latency. Apple calls it network responsiveness. They've got a test now built into Mac OS and iOS. And what happens there is you're actually using cross traffic. You're generating traffic. Doesn't have to be an extreme level of traffic, but some level of normal traffic, while then also doing that latency, that round trip test. And what you find is that you're going from, say, tens of milliseconds of idle latency to hundreds or thousands of milliseconds of working latency. And that's the difference between a game getting sort of glitchy, video conferencing occasionally dropping, and so on. And I'll talk more about some of that in a second. I think we're all familiar with that. We had lots of customers at the early phases of the pandemic, as an example, suddenly switched to working from home, like all of us did, and they might have had gigabit service or even fiber to the home, but they still encountered working latency problems. So it wasn't a bandwidth issue. It was a latency issue, and quite frequently, latency in their wireless network in the home. And so from a design standpoint, a lot of times people thought that you had this trade-off. You could either have very low delay in network delivery, or you could have very high throughput. And this notion that's coming out of the TSV working group, transport working group at the IETF, is that you can really have both of those things simultaneously, but it requires some novel changes. The other thing to mention is that often folks think, oh, this is just like a metaverse thing. This is just AR and VR. And so, I don't have a Vision Pro yet, so who cares? The reality is that anything that is interactive will benefit from ultra low latency dual queue networking. And so that's anytime a user is in front of a screen or interacting with a device, even if you're talking to Siri or Alexa, those kinds of things where there's some delay over the network, having that be faster is very important. And we think, much like the sort of first era from narrowband to broadband, where you have all this network capacity available, all this bandwidth, suddenly applications develop to take advantage of that. We think there'll also be similar types of development once dual queue is developed and out in the wild a little bit more. So let's look at this wonderful probability distribution. I think a lot of us focus on propagation delay, so speed of light, and interface delay. That might be PON or DOCSIS or Ethernet, what have you. Those are very controlled. They're generally pretty bounded. You know, if you've got like a really long route someplace where you've got a shorter route, and it is what it is. In most networks, to the end user, if an end user is going to run that test over PON or over DOCSIS, for example, that's going to be on the order of 10 to maybe 20 milliseconds at the outside. And you can't really go, below that idle latency measure. But the queuing delay, that IP queuing delay that occurs at a bottleneck, and I'll dive into that in a second, is really where this huge variation is. And a lot of applications, think about video conferencing or online gaming as another great example, really has trouble adapting to a lot of variability in that delay. And that's what actually happens when you're using the network. A good example might be you're on a video conference on Zoom or WebEx and what have you, and you're also opening up a browser and you're looking at a website, or somebody else in the home happens to do that, or they're uploading something to iCloud. A browser session, as an example, might open 9 or 10, maybe even more connections. All those connections end up taking away network resource from that real-time flow, and it suffers. And so queuing delay is really important, and we've studied this across all types of access methods, including fiber to the home, and you see that is an issue. And again, the order of that is hundreds of milliseconds, if not more, given that you're often doing multiple round trips to prepare a web page, to load an app on your phone, or what have you. So diving into dual queue basics, the first thing to understand is that there is always a bottleneck link on the end-to-end path. And even if you have fiber to the home, there's a bottleneck somewhere. It's probably in your home network. It's probably either in your Wi-Fi LAN, or it's in that CPE that's the demarc between you and your ISP. And ultimately, there have been lots of TCP congestion controls that have been developed over time. Some of the recent ones, like Pi and FQCODL and so on, have done a great job of trying to use sort of one network queue and being able to harmonize across different types of interactive as well as queue building traffic. But ultimately, the part of the TSV working group went off and worked on this project for a while and essentially concluded, hey, what if there was an alternative, which was that we have two distinct network queues at those bottleneck links. One queue, which is the classic queue for normal queue building traffic, whether those are web pages or file transfers and so on, where people are not really sensitive to the amount of time. And another, which has a very shallow queue and is optimized to real-time and interactive types of traffic. And so that's what has ended up. There are 3 RFCs for L4S, which have just come out. I'll dive into this a little bit more. And there's some other internet drafts that are sort of finalizing the second part of that standard, or an extension-related part of that standard, that are coming soon. Some good things from an architecture standpoint that I like personally is that first, it can be incrementally deployed to start to see the benefits. So unlike a lot of technologies where you need everybody to embrace it and deploy it for you to start to see returns, that's not really the case. Comcast, for example, could deploy this technology in our CMTS and our cable modem and work with some application vendors like Apple that mark their traffic for this, and I'll explain exactly how that works. And our users will start to see a benefit immediately. It doesn't require all the other applications, all the other CDNs, all the other ISPs to implement. The other is that there's very loose coupling between the layers. And so in this respect, I mean, there doesn't have to be knowledge between the application level and the network level, meaning no direct communication. I don't have a special API for every application provider. You don't have to sign some legal agreement with me, et cetera, et cetera. The contrast might be kind of 5G network slicing, which, there's a high degree of coordination between a mobile network operator and an app provider that's originating packets. So loose coupling and incrementally deployed, architecturally, those are usually working in your favor for eventual deployment. Some other principles are that only the applications mark traffic. So when a client is originating their packets, they're going to mark their application header, and I'll tell you their packet header. I'll tell you exactly how that means, or excuse me, what that means. It's not the access network that does it. And this was sort of the middle box conundrum, from the past where DPI was used, or where, as many of you that are last mile ISPs know, there are countless vendors coming to sell you a magic box that can peer at your traffic and infer what needs what treatment, and it happens wonderfully. And I can tell you from a little thing called the BitTorrent incident way back when in the Comcast network, that doesn't work very well. Definitely not a good thing for middle boxes. Great to have applications marking that traffic. In addition, if you think about the innovation cycle of those two areas, the innovation cycle of network equipment is much slower than how fast application clients are iterated and updated. And so even if in a middle box, you came up with a great way to infer a certain type of traffic and know, okay, 100%, I can always identify this is WebEx traffic. The problem is the WebEx developers are every single day pushing updates to those clients. And so you've immediately diverged from that point of time, and that client is off on some other permutation, and your inference accuracy goes down over time, and pretty distinctly. So we're going to talk then about this bottom point for this particular audience, which is about what network operators need to do to make this happen. And I've got some things that'll go into that. One thing that I want to mention before I do talk about the marking is that a lot of this goes to how TCP congestion control works today. I think we all understand this classic sawtooth pattern, and that essentially is a control loop. That's a feedback loop from the sender to the client, or the destination, between those two ends of a flow, to say, wait a second, I don't have as much bandwidth, back up, or I back off a little bit, or I have more bandwidth, keep trying to ramp up. And they call it slow start for a reason. As you ramp up to that capacity, it's fairly slow. It takes multiple round trips for you to get up to that full capacity of your link. And conversely, a few round trips to back off, even though the back off is a little bit faster in many cases. And so as various active queue managers have been deployed, some of the buffers and the targets have been lowered, and AQM, which is part 3, that's deployed in a lot of our cable modems as an example, that still provides pretty good performance. But what you end up with when you get into L4S, which is one of the standards, again, I'm going to go into this in a second, that essentially creates very, very fine sawtooth. So you're seeing an immediate one packet back, providing knowledge to a sender to sort of back off or speed up. And so that basically accelerates that control loop and allows a much more responsive network experience. So there are two types of dual queue networking that the IETF is specifying. The first are the first 3 RFCs do the top one, which is low latency, low loss, scalable throughput, or L4S for short. And it's intended for not just flows that are interactive, but flows that also might want to use a high bit rate. So it might be a video game, it could be an augmented reality kind of thing, whatever it might be. Video conferencing is another really great example because you've got a video stream coming down to your client. And the requirement there is, first, on the server side, you have to run some kind of a responsive congestion control. So going back to this slide, you need something that can react to the control signals that there is congestion, for example. And so that requires, right now, TCP prog as an implementation. You can run that on Linux if you want to. And there's more to come there. Apple's running it on some of their servers that we're testing with. And I'll share some of those stats in a second. But that's important. And so in terms of the marking that's used in the packets, this uses the ECN header of the packet. And the default marking is ECT1, which really means, hey, I can do L4S. I am capable of L4S. If it sees a congestion event, it marks it, changes that ECT1 to CE. That stands for congestion experience. Pretty simple. And that happens right away. And I should also add, any hop along the path can also add a CE mark if it sees congestion at that hop. And that sender and receiver should automatically and quickly adjust as a result of that, which is great. One of the good parts about the ECN header is that almost no network operators bleach that part of the packet. That's not to say that there aren't some that do. Some of them might be in this room. But it's worth looking at. We actually found a very, I would say, humorous problem with this, where we were running a test for this in our network. We thought, we don't do this bleaching because we had a test that was looking at it. It was only testing in one direction. When tested in the other direction, we're like, it's bleaching. Okay. And we updated every single one of our cable modem configuration files over a weekend. So that was a thing. The other is the second option here is non-queue building. So there are some internet drafts that describe this. I can't remember, the rev number that we're up to. It's certainly almost 20, if not more. I don't know, Warren, if you've ever had that many iterations of a draft you've written, but it's like, it drives you insane after a while. It's like, okay, last call for the 5th time. And then someone one day before the end of last call is like, oh, wait, here I have 53 comments. Please read these and adapt to it. So, I'm glad I'm not an author or editor of that document. But I'm going to buy definitely a few beers for that person when the RFCs issue. But non-queue building is essentially for low bit rate traffic. Think of DNS queries as an example, would be one. So there are a lot of types of traffic that are in that kind of category. No requirement on the server side. So that is sort of one of the benefits. You could implement this on the client and not have to do anything on the server side, which can, be helpful in some respects. The downside, which is a big one, especially for this group, is that it uses the DSCP field of the header, which means that it would be the first real internet-wide case of interdomain DSCP marking. And I know that talking to lots of diff-serve people from the past that came up with those things, their dream long ago was that there would be all these common DSCP marks across boundaries. And as it turns out, that is just not the case. And every network, as you all know, has their own sort of way to use DSCP marks and so on. This is going to be the first one, which is DSCP 45, that we want to work across domain boundaries. And so I will just ask folks here, go take a look at your router config, see if that's a mark you can free up. It may be the case, and the internet drafts describe this, where if you're already using 45 internally for some reason, you can just do a remapping of that as it comes in, ingressing into your network. So instead of on ingress, bleaching that out, just transform it to some other mark that you could do for the same thing. And then when it gets to the client, you can mark it back to 45. And that's what we're doing as an example. So we're in field trials right now. We started field trials with customers. Remarkably, it was the highest interest level of a customer field trial we've ever had, which surprised us. Usually when we get dozens of customers that are interested and engaged, we're like, hey, that's awesome. We had thousands of people that were interested, which was great. We were able to very carefully select the people that matched the technical criteria that we wanted. We, through the testing, have not noticed any bandwidth starvation of that classic existing queue, which was a positive for us. That was certainly a worry. We had one app that we had excessive CE marking. We actually found a way to fix that, so we just deployed an update of our configurations about a week ago. And we've noticed, in particular for cloud-native gaming, as opposed to console gaming that has a cloud component, so sort of cloud-native applications, they seem to have a bigger improvement level than more traditional applications. And it may just be because they rely on everything being network-based rather than some aspect of that being on a very heavy, compute-capable client, for example, like a PS5. And we're doing lots of continuing trials. So, here are some stats in terms of when we started. The interdomain test we did was with Valve, with some of their Steam games. That was a big deal. Very few people in our technical organization understood why that was a big deal, but we were all super geeked out about it. And it is what it is. So that continues. In terms of our latency that we're seeing, we see about a 50% working latency reduction so far. And this is through a synthetic test that we have running in our gateways. With our newest cable modem config that we pushed about a week ago, we think we'll see more than that. But that's just a synthetic test. That doesn't really tell you much. And this is sort of one of those things that's interesting. Because of the rise of encrypted traffic, it's really hard for us to infer user quality from that encrypted traffic. And that's by design, right? That's a good thing. And so we've partnered with a bunch of different application developers. We've got, I mentioned on the last slide here, Valve for their Steam games, NVIDIA for their GeForce Now platform, and Apple for FaceTime. We've been testing with them and then asking them, would you please, for this set of customers, tell us what the QoE is that you see on your side of things and what do you see on your server? And so that's been very helpful. So GeForce Now, this is one of the best proof points for us. They went from seeing lag spikes for our users, even with active queue management turned on, of around 225 milliseconds to 20 milliseconds. And that tells you two things. Number one, they've indicated that, north of about 150, 200 milliseconds on online gaming, that's the difference between sort of dying in the game and not dying in the game, right? That's like a big deal. And when they've done some videos, I don't have the videos here, I just got them from them yesterday. What you really notice is that there's a lot of stuttering in the game. So like they have one video where you're playing Fortnite and you're moving around, through the game, and the one where there's background traffic, competing traffic on the LAN, and there's not L4S, you're noticing the player sort of every once in a while skips ahead, and it's like a little bit of a beat where this the thing moves across the screen, and it's a little bit off-putting. And if you're doing like AR or VR, you're actually going to get motion sick in those kind of environments. But the other thing that you can see is that all of those vertical spikes where you'd have that variability of every once in a while you'd have a spike, that went away, and you had this really nice consistent latency. And that consistent latency is what a lot of folks, especially video conferencing platforms, will tell you, they don't necessarily need the absolute lowest, 10 millisecond latency, but they want it to sort of get to a place that's low and just stay there consistently, so that the application can adapt to that. So, we think it's a big deal, NVIDIA was delighted by it, that's a big deal. The other one is Valve, and so we have the top one with the little circles. That's what happens under load without L4S. And what you see with the triangle is what you come down to with L4S turned on. And in this example, you're coming down, again, almost to what idle latency looks like on that connection, which is a great, great deal from a performance standpoint. So we were, again, really excited about that. They were too. And to be honest, in both these cases, we were getting paid to play games in the lab. Like, that's like super awesome. It's like my kid, who was 16, he couldn't believe it. But, it is what it is. It's an aspiration, I guess, for him to study technology stuff. So in terms of what we're doing next, this is my last slide. We are continuing field trials through next month, and then we'll see what happens. I can't say more than that. But I can say that operationally, we are preparing to scale to millions of subscribers that will have this capability this calendar year. So we think that's a big deal. And I mention that because this is one of those standards, like a lot of IETF standards, that benefits from network effects. The more people that adopt it, the more value there is in that standard, right? So a lot of my time is being spent talking to application developers and network operators like here at Nanog to get other people to embrace it and adopt it. But in the short term, I won't, I don't think I'll mind competitively if I could eventually run an ad and say, the experience of cloud gaming on my network is way better than on my competitor's network, and market that to, competitive gamers or people that work from home or so on. So I won't mind a short-term, head start in the market, but eventually we want everybody to embrace this in terms of marketing. So in terms of network operators, which is most of you in this room, if not all of you, I think that there are really two things to do. The first is to look at the ECN headers, look at your router policies, and are you bleaching ECN? And if you are, fix that, please. And if you are not, then great, you get a gold star. We really appreciate that. And a lot of the testing that Greg White from Cable Labs has done across a lot of networks, most networks do not bleach ECN, which is good. I think there's still one fairly sizable North American network. I've already reached out. You know who you are. I know you're working on it. Keep going. And we'll see. So that will enable L4S, which is standardized now and is what is behind things like the games that I've shown you and FaceTime as an example. And then the second would be DSCP 45. Admittedly, this is harder, especially if you're already using 45 inside your network. Either way, let's talk about what that means. If you're not using 45, I'm delighted. That's awesome. Basically, update your router config so that you allow ingress packets coming in from the Comcast network or somebody else to pass that mark all the way through end to end. The other would be if you're already using 45 internally, is come up with a transformation scheme. I know there are some older routers, I'm not going to mention which ones, that have a little bit of trouble with that sometimes. But you're probably upgrading away from them anyway. And if not, maybe this will help you to justify that. I'm sure someone will be willing to sell you a new router. You can talk to them out there. In terms of applications and operating systems on the client side, I certainly mentioned in the servers that cloud gaming services like GeForce Now and some of the Valve Steam games are supporting it. The other one is obviously I've mentioned a few times, which is Apple, which has really been leading the way here. L4S is built into Mac OS and iOS. They've, for the past couple of worldwide developer conferences, talked about L4S, and so they have some great videos, especially if you happen to be connected to iOS app developers. They've got some great head start videos and documents to explain how to quickly sort of get to market with your applications, which is cool. So we're expecting more, and I understand, even though I do not yet have a Vision Pro, I'm looking forward to getting one. It is also built into the Vision OS. So should be a big deal. And just to digress, since I have a couple minutes more, and then I'll take questions, to use a competing example of that sort of Vision Pro, Microsoft has a VR headset as well, AR headset, and they had a great contract with the Department of Defense to test this for like the next generation soldier. Soldiers were wearing these in a simulated battlefield, and they were using it. It might show like, augmentation about maybe where other soldiers were, or threats were, what have you. And they were all getting motion sick because of the delay between what they were seeing through their lens and the way things were represented. And it's funny because that is quite obviously a latency problem. And it's even funnier because you would imagine this was probably like $1 billion contract, right? Probably a super pristine network that they were all practicing their war games on, right? And yet they still had latency problems. So not that that's the first application I would argue for necessarily. I like the gaming one better, but I think there are lots of examples where that comes to the fore and people don't realize what the real issue is. So with that, happy to take some questions, and if not, I'll jabber a little bit more.
Oh, it is actually on.
There you go.
Weird. So at the beginning of the talk, you said when the pandemic came around, a lot of people had sadness because the wireless didn't work.
Yep.
For things where you run the cable modem and you run the wireless, you can fix that. How do you get the existing people who've got their own cable modems, their own wireless stuff, etc.? Like, might you help fund wireless people to put this in the code? Or?
Yeah, so, it's funny. IEEE and IETF are sometimes two ships passing in the night, and they have different notions of marking and queues and priorities. So it's my hope that eventually those things will harmonize. In the Wi-Fi domain, there are really kind of essentially 4 separate queues: background, best effort, video, and voice. And so when we see an L4S packet come into the wireless LAN, we're actually putting it into the video category, which should provide slightly better treatment. That's a bit of a hack though, right? It's not the best. What we also noticed though with customers, and I would recommend it if you haven't already done it for your own network, is that obviously many people did mesh Wi-Fi networks in their homes. And some of those distributed pods in the house might use Wi-Fi backhaul, right? Use Ethernet backhaul. Please, for the love of God, use Ethernet backhaul. Your experience will get way better. And so we often found we were going through this cycle of, okay, your Wi-Fi gateway is good, but it's in the basement in a cabinet. Okay, so get pods and distribute Wi-Fi in your house. Okay, now do Ethernet backhaul, and sort of by increments, taking some of that away, but also coming up with the method to sort of pass that marking into the Wi-Fi network, via ACVI helps. Jeff.
Jeff Houston. L4S and this whole ECN marking kind of relies at the application level to restrain itself in the amount of network queue buffer consumption.
Mm-hmm.
So in that respect, if your application is well behaved, it doesn't matter if your network buffers are enormous.
Right.
But if your application is ignorant, and there are an awful lot of them, the sizing is actually really important. And it's kind of an open question, where do you size when you're deploying this?
Mm-hmm.
It seems that the new sort of theory about how big your network buffer should be is the bandwidth delay product divided by the square root of your average number of flows. So if you're actually in the middle of 1 million flows, then you don't do bandwidth delay, you would do 1,000th of the bandwidth delay product. In other words, as you are closer and closer to a busy core, the actual amount of network buffer you provision in any case is relative to the bandwidth delay, smaller and smaller and smaller. How do you provision these days, and how do you think others should be provisioning? Is the old rule bandwidth delay still relevant, or should we actually be constraining a little more?
Well, I'll tell you, it's being hotly debated, and we've
everywhere.
Yeah, everywhere. And I don't think we don't know just yet. I think we're testing out a bunch of different things as we implement L4S. And I would say what surprised us is that in comparison to turning on AQM in the network, which was a very binary on-off, this is a lot more configurable. And so we're really trying to learn from that. A related aspect is, I think a lot of people ask, well, what if every application marks for low latency treatment? And ultimately, I think a lot of applications can benefit from it. Essentially, you're just volunteering to go in a very shallow queue. And it should, on some level, be self-correcting, because if you want to build up a big queue and you've got this big file transfer and you want to maximize the capacity, you should have a kind of crummy QoE if you're marking for low latency, and as a developer, you'd go change that. But we'll see. That's a big debate.
If I was running DBR, how could I say, put me in a tiny queue? Because oddly enough, I'll be better at my social behavior if I get put into a tiny queue, because BBR does an entirely different mechanism of probing.
I mean, I think, the good part is that some of those, AQMs are well behaved, I should say, and there are a lot that are not. And maybe that's what the battle is most of the time.
Thank you.
Yeah. All right. Any other questions? All right. Thanks, everybody. Appreciate your time. Thanks.